Today we're going to discuss the method of substitution and what happens in definite integrals. So let's recall that substitution comes about because of chain rule type problems. So we have here integral from a to b of f prime of g of x times g prime of x dx. And we realize that that's a chain rule, so that's just f of g of a between a and b, which gives us f of g of b minus f of g of a. Now let's try and do this same integral by substituting. U is g of x, du dx is g prime, and du is g prime of x dx. So when we substitute in, we get that f prime of g of x times g prime of x is f prime of u du. Now you'll notice that these limits a to b are not written on this integral, nor are they written on this evaluation. Now what's clear is whatever we do, we better end up with this as our answer. And it makes it pretty clear that the only thing that we can be putting in is something that gives us g of b here and g of a there, which means that there's a g of b here and a g of a there. And that's what the limits on this new integral have to be. And what you'll notice here is u is g of x. So these limits come from the a, b, and x, and they are g of a, g of b, which is what you get when you put the a and b into our substitution. So as an example, let's look at the integral from 0 to 2 of x squared times x cubed plus 1 to the 1/2 dx. We make the substitution u equals x cubed plus 1. Du dx is 3x squared. Du is 3x squared dx. We see there's an x squared dx in the integral, so we divide by 3, and we have 1/3 du equals x squared dx. Okay. Now what we notice is that when x equals 0, u, which is the thing we were calling g of x, is 0 cubed plus 1, or 1. So x equals 0 corresponds to u equals 1. When x equals 2, u equals g of x is 2 cubed plus 1, or 9. So when x is 2, u is 9. And those are the limits that we have for the u integral. The 0 to 2 changed to a 1 to 9. Okay, x cubed plus 1 to the 1/2 has now become u to the 1/2. X squared dx is our 1/3 du. And now we integrate, and u to the 1/2 becomes u to the 3/2 over 3/2, now between 1 and 9. And we do some algebra. Dividing by 3/2 is the same as multiplying by 2/3, so we get a 2/9 u to the 3/2 between 1 and 9, which is then 2/9 9 to the 3/2 minus 2/9 1 to the 3/2, which is 1. And 9 to the 3/2, square root of 9 is 3. 3 cubed is 27. So we've got 2/9 times 27 minus 2/9, which works out to be 52 over 9. An important note, it is wrong to write the integral from 0 to 2 of u to the 1/2 times 1/3 du, as these limits are supposed to refer to the variable in here. And if you gave that to somebody and didn't tell them what the substitution was, they would get the wrong answer. Correct, but not recommended, is after one makes the change of variables, one notates on the limits that these are x limits. You go through the anti-differentiation. You change back to the x variable, and now the x equals 0, x equals 2 can now just be put as 0, 2. And when you're done, you've got 2/9 times 9 to the 3/2 minus 2/9, exactly what we got before. So this is correct, but it's more work than you need to go through. Just transform the limits. Let's do another example. The definite integral between 0 and 1 of x plus 1 over x squared plus 2x plus 2 squared dx. Now here we're going to make the substitution u equals x squared plus 2x plus 2. du dx is going to turn out to be 2x plus 2. And that means du is 2x plus 2 dx. If you look in the integral, you're going to see there's an x plus 1 dx, which is exactly half of that. So 1/2 du is going to be x plus 1 dx. Now we need to worry about the limits. When x is 0, u is 0 plus 0 plus 2. And when x is 1, u is 1 plus 2 plus 2, or 5. So that means in our new integral, x squared plus 2x plus 2 squared has become u squared. X plus 1 dx has become 1/2 du. And the new limits, when x is 0, u is 2. When x is 1, u is 5. And we just carry this out, we carry out this definite integration now with respect to u. We factored a 1/2 out in front and written 1 over u squared is u to the minus 2. Now using our power rule, that's going to give us 1/2 u to the minus 1 over minus 1 between 2 and 5, which we can rewrite as minus 1 over 2u between 2 and 5. At 5, we get minus 1/10. And at 2, we get minus 1/4. So it's 1/10 minus minus 1/4, which is 1/4 minus 1/10. 5/20 minus 2/20 is 3/20. Now let's look at the integral from 0 to 2 pi of the cosine of x over 4 plus the sine cubed of x dx. Now, if this problem had been indefinite integration, this would be beyond the scope of the course. We don't have mechanisms to find an antiderivative for this thing. However, it's a definite integral, and sometimes magic happens. So, let's let u equal sine x. du dx is cosine x, and du is cosine x dx. So we can see here, that's going to be du. This is going to be 4 plus u cubed. But now let's look at the limits. When x is 0, u is 0 from here, because the sine of 0 is 0. And when x is 2 pi, the sine of 2 pi is also 0. And what we get is this integral between 0 and 2 pi in the x variable changes to an integral between 0 and 0 in the u variable. Now notice this thing has entirely transformed between x and u. This trick doesn't work unless that happens. But now what we've got is a definite integral between 0 and 0, and it doesn't really matter what the integrand is. This is going to equal 0. There's no area under that curve. So knowing how to change the limits actually lets us do this definite integral without finding an antiderivative. So this sorts of transformation of integrals is an important thing to know about, so let's practice. So suppose we know somehow that the integral from 0 to 4 of f of x dx is 3. Let's evaluate some related integrals. The integral from 0 to 2 of x f of x squared dx. Now, we're going to transform this integral into something that looks like this integral. The substitution we're going to make is u equals x squared. du dx is going to be 2x. And du is 2x dx. We notice that x dx is in the integral, so 1/2 du is x dx. Now, we're going to transform the limits. When x is 0, u is also 0. And when x is 2, u is 2 squared, or 4, which means this thing transforms as integral 0 to 2 of x f of x dx becomes the integral 0 to 4 of f of u times 1/2 du. And the 1/2 factors out, and we've got the integral from 0 to 4 of f of u du. Now remember what we talked about with dummy variables. It does not matter what this variable is called. It's the area under the f function between 0 and 4, which we know up here is 3. So the answer is 1/2 times 3, or 3/2. Let's evaluate another related integral. The integral from 0 to 1 of f of 4 minus 4x dx. Here, if we're going to transform, we're going to have to let u equal 4 minus 4x. du dx is going to be minus 4. du is going to be minus 4 dx. And minus 1/4 du is going to be dx, which is what we're going to put in for the dx. U is going to be 4 minus 4x. And now we need to worry about the limits. When x is 0, u is 4. And when x is 1, u is 0. So our integral turns into, the integral from 0 to 1 of f of 4 minus x dx turns into the integral from 4 to 0 of f of u times minus 1/4 du. And we factor the minus 1/4 out, and we have the integral from 4 to 0 of f of u du. Now, if you look up here, we've got an integral from 0 to 4. So it doesn't quite match. However, we know what happens when you flip limits. And when you flip the limits, it changes the sign. Minus times minus is plus, so we've now got 1/4 times the integral from 0 to 4 of f of u du, which is going to be 3. So we've got 1/4 times 3, or 3/4.